In this video, we're going to discuss the classical limit of quantum mechanics. So quantum mechanics has a lot of strange behaviors that seem to contradict our experiences on the macroscopic scale. However, we believe that quantum mechanics reduces back to classical mechanics whenever we approach systems with higher energies or larger masses, and therefore get to systems that behave more macroscopically like the world we live in on a day-to-day basis. This is called the classical limit. So we've already seen, for instance, that you get wave-like behaviors of macroscopic objects, that is, objects with large masses, that are very hard to see. So if we compare the de Broglie wavelengths for an electron moving at a fraction of the speed of the light, we see that its wavelength is on the order of something like 2 angstroms, which is similar in magnitude to the size of an atom. On the other hand, a baseball moving at 40 meters a second has a de Broglie wavelength of 10 to the minus 24 angstroms, so it's 24 orders of magnitude smaller than your typical atom. And so clearly that sort of wave-like behavior won't be observed. Quantum mechanical objects also behave more classically at high energies. To see this, consider a particle in the box. The potential energy inside this box is uniform. It's zero everywhere in the box. And so from a classical perspective, you would think that the particle inside that box would be equally likely to be found in any part of the box. There's no particular reason it should prefer the side of the box or the edge of the box or anything like that. And so you see the figure on the right showing the probability distribution for the particle in the box. However, on the left we show the probability distribution for a quantum mechanical particle in the n equals 1 state for the particle in the box. And you can see that this probability distribution is non-uniform. It shows an increased preference, an 82% chance in this case, of finding the particle in the middle half of the box rather than either the left quadrant or the right quadrant, compared to 50% chance of it being in the middle of the box in the classical case. However, as we increase n, that is, as we go to higher energy states, the probability distributions for finding this particle become more and more uniform. So you can see here in the n equals 1 state, we have a strong preference for finding the particle near the center of the box. However, already by n equals 5, that probability is starting to be distributed across the box. By the time we go to n equals 50, you can see now the probability is getting much more uniform across the box, and at the n equals 500 state, you essentially see we've regained an almost perfectly uniform probability distribution of finding that particle anywhere in the box. So in other words, as we head to these higher energy states, we see that the expected classical behavior is emerging out of the quantum mechanical predictions. In other words, quantum mechanics, despite many of its strange predictions, is not contradictory to our macroscopic experiences.